The next example we're going to look at in section 2.2, and this will be the last one for this part, is a very, very important example. This is example 5. And one of the things that it kind of illustrates is that, from your past experience, especially from Calc 1 and Calc 2, is that when we tell you to find like an antiderivative or even like a definite integral for that matter, the types of functions that we're working with are very, very special in that we're actually able to do so. Not every function has, however, an elementary antiderivative, and that's kind of indicative of what's going to happen here in example 5. This is another separable differential equation. You can multiply both sides by the dx, as we normally would. We would get dy equals e to the negative x squared dx. The next step would be to try to go ahead and integrate both sides. We can integrate the left-hand side to get y. That's not an issue. But now we run up against something like this. E to the negative x squared dx, even though it's a basic function, right, it's just e composed with a polynomial, it does not have an elementary antiderivative. There's no, kind of basic function whose derivative is e to the negative x squared. However, symbolically, what this would represent would be a solution to our differential equation. So when that happens, when we get into the rare circumstance where we actually can't do the integration to get an exact closed form solution, what we're going to do is something a little bit different. So we're going to introduce a dummy variable in this case, and I'm just going to use the dummy variable t. So let's think of y as being some function of t. So we have dy dt is equal to e to the negative t squared. And now what I want to go ahead and do, so everywhere we see an x, we're just kind of putting a t. And now what we want to do is we want to integrate both sides dt. And because ultimately we knew that it was a function of x, we're going to do a definite integral here where we're going to integrate from, in this case because I have an initial value, we want the x to go from 3 to that arbitrary value x and from 3 to x. Here, what is the antiderivative of dy dt with respect to t? Well, that's going to be some function y of t. And then we have to evaluate it at the bounds of integration. That's going to be 3 and x. And then this is equal to this thing on the right-hand side. Ultimately, if we could do the integration, what we would end up with would be some function of x. But we can't actually do the integration, so we're just going to symbolically leave it like that. It's going to be the definite integral from 3 to x, e to the negative t squared dt, where kind of like our dummy variable t was a variable of integration, and at the end of the day, when you evaluate this definite integral at the upper bound, that will still produce and leave us with a function of x. So on the left-hand side, we have y of x minus y of 3 from that part of the definite integral is equal to the definite integral from 3 to x of e to the negative t squared dt. This thing we actually know from our initial value condition, y of 3 was equal to 5. So we have y, and I'll show the explicit dependence here, y of x minus 5 equals the definite integral from 3 to x squared e to the negative t squared dt. And then we can simply add 5 to both sides to get the following. If my pen doesn't disappear. There we go. 3 x squared, excuse me, not x squared, blah. Where did x squared come from? It should be x. X was our upper limit of integration. E to the negative t squared dt. So this is kind of a really profound moment, kind of a really kind of important development in terms of like the mathematical knowledge that you've accumulated up to this point. we're going to start to, especially in this class, there's going to be special types of functions where their definite integral or their antiderivative will be the solution to a differential equation. However, they might be one of these special types where we actually can't physically find the closed form expression for that function. Yet, nonetheless, we're going to get used to kind of working with their integral representation, because at the end of the day, and I claim, and I'll actually show it this one time, remember, we're saying at the end of the day that this solution, this function, y of x, is a solution to this initial value problem. In other words, I'm claiming that the derivative of y, first of all, it's equal to e to the negative x squared, and I'm also claiming that y of 3 is equal to 5. Well, let's go ahead and check that. So, again, and I don't doubt any of you or begrudge anybody for being a little bit skeptical that this thing actually works, but let's check it. First thing let's do is let's check the initial condition, because that's the easiest. If I plug 3 into this function, do we get the output 5? Well, this is going to be 5 plus the definite integral from 3. Again, everywhere we see an x, we're putting 3. So it's the definite integral from 3 to 3 of e to the negative t squared dt. And as you should have known from previously, when you do the definite integral from a to a, that result gives a 0. And so we get 5 plus 0, which is 5. Okay? So that part checks out. The only other thing we need to see is, does the derivative of this function give us e to the negative x squared? So if I do the derivative with respect to x of y of x, this is equal to d dx of 5 plus the definite integral from 3 to x of e to the negative t squared dt. First of all, the derivative of a constant, that part's going to be 0, plus, and now we're going to differentiate an integral. This is fun. So the question of the day is, what is the derivative with respect to x of the integral from 3 to x of e to the negative t squared dt? And this is going to follow directly from the fundamental theorem of calculus. Recall that differentiation, definite integration, differentiation and definite integration are inverse operations. So this is going to give us back e, but not e of t. It's going to give us e of negative x squared. And that's what we claimed it was supposed to be. And this is from the fundamental theorem of calculus. The fundamental theorem of calculus, I believe part 2, it said the following. The derivative with respect to x of some numerical lower bound of x f of t dt is simply that integrand evaluated at the x variable. So we just kind of swap out the t for x, and we get exactly what we claimed. Okay. So that expression, I just erased it. But y of x equals 5 plus the definite integral from 3 to x of e to the negative t squared dt. That is the solution to our initial value problem.